ridiculousness I have going on today. Because let's be fair, that's pretty much how I roll. And I feel like that's the only way to really roll. All right, it's all about that base. We're learning to work with bases other than E. We'll be successful when we can do the same things, but with other bases. Hey, knew it. All right. So what other bases can we have besides E? I don't know, basically any other number. We generally, if you remember from pre-calc, we talked about that, like for logs, we like that base to be a positive number. It doesn't have to be. Remember, we could let the exponent, the A, B, we could let this A become negative. But if we do that, we're gonna have a giant foray into complex numbers. And while that's totally fine, it's beyond the scope of Calc 1. It's more like, what is it officially? I call, after I took Calc 3, I had opportunity to take complex analysis, which is where we dealt with calculus with complex numbers. So it's like further down the road. And that's the first time I learned how to take like the 1.67th power of a negative number of like -2. So we'll pump brakes. Like that's the first time I learned how to do that. So I'm just saying, again, we can do it, but there's a lot of learning and things we need before we get there. All right. So we're going to let A be positive. So we're probably going to redefine these, huh? Yup. Avi. So a to the x, again, everything's basically in terms of natural log. We're redefining everything in terms of natural log because that's how our book does it. So a to the x is really just defined to be e to the natural log of a times x. And I can show you like why that's equivalent in just a moment if you don't see it right away. And log base a of x, we're redefining like this. Now this is essentially defining log base a of x using the change of base formula. That was something that we spent next to no time on in pre-calc because we generally we don't need to use it very often. But it's just a formula to look up. And this is literally the change of base formula. Now this over here, we set it up like this because then it's like it's a constant times natural log. All right, a constant times a changing function, a variable function. Or this would be a constant function. This is a variable function. All right, so that's how we're going to set these up. Would you like to see why this equals a to the x? Yes. A couple brave people said yes, they do. Why not? Okay. You're just making my day there, folks. Sweet. So this could be rewritten because I have exponents multiplied together here, right? So this could be e to the natural log of a to the power of x. E to the x and natural log are inverses, as we saw in 5.3 and previously, 5.4 actually, I think. Anyways, they're inverses, so this inside piece just becomes a. But we still have the power of x due to the properties of exponents. Thank you so much. I was really hoping someone would say yes, and I had a couple people say yes, and I'm very excited about that. That makes me rather joyous. But that's it. It's just like a freaking clever little way to make that happen. Remember, it's just that remembering that when we have two exponents multiplied together, that is, we can leave it like that, or we can break it back apart as the exponent to an exponent, okay? So fun facts. Oh my gosh, I'm very happy we got to talk about that. And this is literally just change of base formula. There's nothing else to really show. That's right. I knew I would put her in there somewhere. All right, so I probably remake this table at some point. This is just a screenshot from an old presentation. I should remake this at some point, but it's probably not going to be this time. So anyways, these are important things to remember. The properties of exponents, right? In fact, I used this fourth property, the power property, when showing you why a to the x is equal to e to the natural log of a times x. All right. Also, each property of exponents has a related logarithm property. All right. So properties of exponents, properties of logarithms. Maybe I should say laws of exponents, laws of logarithms, or logarithms. That was very terrible. It's okay if you want to boo me for that one. Anyways, these are some different properties of exponents and logs that we should know. There are things that we spend, exponents, we literally introduce them before Algebra 1, but we spend more time on them in Algebra 1. Like we see them in 8th grade math, we see them in Algebra 1, and they just keep popping up a lot, and we use them a lot. It's just something we need to know. And part of that is because we're trying to set the foundation for logarithms later on, but also like exponents in and of themselves. Golden. So since we're doing logs of different bases, we probably should see what are the derivatives and antiderivatives of each of these. So the derivative of natural log, if you remember, is just 1 over x. So what's the derivative of log of a, log base a of x? Well, let's go back real quick. Log base a of x is just 1 over the natural log of a times natural log of x. That means that's just a constant. So the derivative of log base a of x is 1 over natural log of a times 1 over x. Because log base a of x is defined as 1 over natural log of a times natural log of x, right? So that's why it's set up that way. So what's the derivative of this? Natural log of a times a to the x. Because again, we could look at it as how we had it defined earlier. Because a to the x, let's see if I can roll back right here. When I look at it like this, the derivative of e to the natural log of a of x is going to be e to the natural log a of x times the derivative of this exponent, which is just natural log of a. That's why we get this. Because again, a to the x is just e to the natural log of a of x times x. All right. These two are super important. They're new-ish to you. They're just kind of new skins, more or less, for the characters you already have. So those are the derivatives. What about the antiderivative of log base a of x? We're not going to deal with it. You learn about, it's something we have to use what's called integration by parts in order to figure that out. So that's beyond the scope of this class. You don't have to worry about what's the antiderivative of log or natural log for that matter. We are not doing the antiderivative of natural log either. But we use natural log for differentiation when we have like 1 over x or 1 over u. Okay, so we still use natural log for antiderivatives and logs for antiderivatives, but we don't find the antiderivative of natural log or of log base a of x. We're not doing that because we just we're not going to go into that process. We could if we have more time at the end of the year and we do our projects and we're like, twiddle thumbs, what should we do? We'll learn some more and we'll do this integration by parts, which it's honestly really cool. I really like integration by parts. I think it's really cool because one of the simple earliest rules we do for derivatives is product rule. And basically integration by parts is undoing part of the product rule. It's just trying to figure out what part of the product rule I have and messing things around to make it work. By the way, the antiderivative a to the x is 1 over natural log of a times a to the x plus c. Which again, if you look up here, if I just have a to the x, I must have been dividing by that, because if I take the derivative of a to the x now, I would multiply by natural log of a, which boom, that would take care of that. Alrighty. Okay. As you can tell, I had a lot of fun. I have a lot of fun making these. All right. That's it. Is it? You can use your graphing calculator to help you out with these. Again, it's just mostly with your graphing calculator. Since we'll probably be doing it in person, the test in person, the AP test in person, you're going to want to make sure you're practicing with that graphing calculator. All right, there is a lot. And so I'm pretty much going to stop talking now so you have a decent amount of time to get going on it. But the most of it is just playing around with properties of logs and exponents, making sure you're really familiar with logarithms of a bunch of different sorts. So again, just making sure that you're very careful. It's 1 through 16. Yes, every single one, 1 through 16. It is a lot. That's why I'm stopping talking right now. And then 28 through 40, that I just want evens. If you want to do all of them, by all means, but I would rather you just do evens. And then there's a couple others for you. Again, with any of these, they're due soon. I think tomorrow is 2 weeks into the semester, into the quarter in particular. I'm going to try to put some points in for things that you've given to me already, just so that it's like, hey, class, why is there nothing in your class? Oh, I don't know, IDK. Basically, it's if you haven't heard the term, it's a CYA tactic. Yeah, we'll do a Jamboard tomorrow to ask questions about 5.5. And if we exhaust our questions for 5.5, then we can just do questions about anything else. But that's the plan. And then next week, Monday, we'll probably start 5.6. So that's our general plan. Oh, yeah, there's a couple extra things you can read about. I'm not going to spend time reading through those.